Welcome to lecture 14. In this lecture, we're going to work on some examples of Kirchhoff's laws. In this example, we're going to use Kirchhoff's laws to find the current through each of the three resistors shown in this circuit and the potential across each resistor. As a homework problem, you might try to solve this problem using the equivalent circuit method. Both methods will give you the same answer, but just two different ways to get there. So when solving a Kirchhoff's law problem, and I think we'll really take our time going through this just to get an idea of all the steps and the method. When going through a Kirchhoff's law problems, one of the first things you should do is identify the current in each branch of the circuit. And then for each of those currents, you'll give them a label, generally I1, I2, and I3, and so on. Another thing you need to do is identify the loops. We know Kirchhoff has two laws, and one of them is a loop law. So we're going to want to identify loops. And number 3, we're going to write Kirchhoff's two laws. So Kirchhoff's current law or junction rule, and Kirchhoff's potential law or loop rule. So there's the overall strategy. Why don't we get started by identifying the current in each branch. We'll do that first. So the first thing we know is that current comes out of the positive end of a battery. So we're going to draw it coming out of the battery, goes through the 280 ohm resistor, and keeps flowing until it hits a junction. So when it gets to this junction, that's where it's going to be forced to split up. Let's label this first current I1. So when the current gets to that junction, it's going to split into two parts. Part of it is going to go straight on through. So let's draw the straight through part. It's going to come around the curve and go down through the 300 ohm resistor. Let's call that current I2. And part of the current is going to go down the branch through the 200 ohm resistor. Let's call that current I3. We've got step 1 done in our problem now. I think the next thing we'll do, we may not do this in every single problem we go through, but let's do it in this one because it's really nice and illustrative, and it's going to help us when we think about potential increases and potential decreases. We know that when current flows through a resistor, the flow is a result of an electric field established across the two ends, and current flows from the positive end with the high potential to the negative end with the low potential. So let's look at our pictures and let's label each of our resistors with the positive end and the negative end. And we'll label those ends by thinking about the way the current is flowing. Okay, we've got step 1 done. We've identified the current in each branch. Next, let's do step 2. Let's identify the loops we can use in this problem. Let's identify the loops next. So the loop is just one loop of your circuit, essentially. In our picture here, there are 3 possible loops we could take. I'm going to put one loop in the left-hand branch of the circuit. Notice that when I draw my loop, I assign a direction to it. That tells us which way to come around the circuit as we add up the potentials. So our first loop we'll call loop 1. We'll do that one in green. Our second loop, let's do that in purple and we'll call it loop 2. I'm going to choose the right-hand branch of my circuit to be loop 2. And I'm also going to come around that guy clockwise. A third loop you could pick, and you wouldn't need to use all 3. For this problem, you can solve it with 2 loops. A third loop you could pick is the whole outer rim. So this is also a possible loop that you could pick. It wouldn't give any new information since it really just combines loops 1 and loop 2. But there are different ways to look at the loop, and one way is not more correct than another way. So now what we've got done is we've identified our currents, we've identified our loops, and our next step is to write our laws, Kirchhoff's current law and Kirchhoff's potential law. So let's start with the current law. The current law says that the net potential into any junction is I mixed that up. Kirchhoff's current law says that the net current into any junction is equal to the net current out of any junction. We've already highlighted one junction in purple, so let's stick with that junction and let's write our current law at that junction. The current that goes into that purple dot, we labeled I1. And we have two currents coming out, so the total current coming out is I2 plus I3. Okay, next we have to do the loop rule, and we'll do the loop rule for each of the two loops. So for loop 1, we're going to have the potential of the battery, delta V of the battery, plus delta V of the 280 ohm resistor, plus delta V of the 200 ohm resistor. And all those delta V's added together is going to give us 0. Now, we don't necessarily write it in this form every single time. I'm starting from scratch in this problem because it's the first example we're doing. When we write our potentials now, there's a couple of things we're going to remember. We're going to remember that sometimes potential is positive and sometimes potential is negative. Potential is going to be positive when our loop takes us in the direction of increasing potential, and potential is going to be negative when our loop takes us in the direction of decreasing potential. So anytime we go from negative to positive, that's an increase in potential. Anytime we go from positive to negative, that's a decrease in potential. In general, what we're going to see is that our batteries have positive potential and our resistors have negative potential, but you have to be super careful because it depends on the direction or the orientation of your loop. Now, I said there were two things we were going to do. What was the other one? Oh, yes. We'll have to use Ohm's law that says V equals IR. So for the battery, the potential is usually easy. It's frequently given. For each of the resistors, we're going to write current times resistance. Okay, let's put these ideas together. As we look at loop 1 and we look at our battery, we see that our loop goes upwards through the battery, goes from negative to positive. That tells us that the potential of our battery is positive. So plus 45 volts. Now, plus the potential difference of the 280 ohm resistor. We go from positive to negative, that's towards decreasing potential, so that's a negative. So there's a potential drop across that resistor when we go in the direction of the loop. Our loop takes us from a positive to a negative. To write down what that potential is, we're going to do the current, which is I1, times the value of the resistance, which is 280 ohms. Then we have our 200 ohm resistor. So through our 200 ohm resistor, our loop takes us down as we follow the direction of the loop. So it comes down this way. As we go down, we go from positive to a negative. That's decreasing potential. And the label for that current was I3. So the potential drop across that resistor is I3 times 200 ohms. If we pause for a moment and take stock, we see that we have our current law gives us an equation with I1, I2, and I3. Our first loop gives us an equation with I1 and I3. If we had another equation with I2 in it, we could solve those three equations together. That equation is going to come from loop 2. Let's see if we can squeeze loop 2 in on this slide. So for loop 2, we have the potential of the 300 ohm resistor and the potential of the 200 ohm resistor. When we add those two guys together, we get 0. Our potential of our 300 ohm resistor, if we look at the orientation of our loop for our 300 ohm resistor, our loop takes us down from positive to negative. So as we go through the 300, our loop is going down from positive to negative. That's a drop in potential or a decrease in potential. So we have minus I2, because the current I2 runs through the 300 ohm resistor, times 300 ohms. Now, the next one's interesting. As we look at loop 2, it goes upwards through the 200 ohm resistor. Loop 2 takes us upward in that branch, takes us from negative potential to positive potential. So as we come around in the orientation that we drew for loop 2, that's an increase in potential. So that's a plus. So the potential increase in our loop is going to be the current through the 200 ohm resistor I3 times 200 ohms. They sum to give 0. Now that makes perfect sense. As we go around a circuit, there has to be a net change in potential of 0. So our loop takes us through a drop in one resistor, so the loop must also take us through an increase in another resistor. Now we have a third equation with I2 and I3 in it. Now we have enough information to solve our problem. From here, it's just going to be solving the algebra. As we go through our algebra now, what we'll do is let's solve our equation from our loop 1. Let's solve that for I1, and we're going to plug that in our equation for our current law. Then we'll come to our equation for loop 2. We'll solve that for I2. We'll plug that guy in as well, and then we'll be able to solve our problem. Okay, so looking at our loop 1 equation, we see that I1 times 280 ohms equals 45 volts minus I3 times 200 ohms. If you prefer to leave it your units here just because visually it's a little bit cluttery, that's absolutely fine. Just make sure you do work in SI units and you include your units at the end when you're finished. So we'll divide both sides by 280 ohms. So we've got 45 volts over 280 ohms. Subtract I3 times 200 ohms divided by 280 ohms. Okay, so 45 over 280, that's 0.1607 volts over ohms, that's an amp or an ampere, minus I3, 200 over 80 is 5 over 7. Like I've said before, I'm more of a fractions person, so I'm going to leave it as 5 over 7. If you prefer to put that in as a number, then absolutely no problem. Okay, so there's an equation for I1. Now let's get a similar sort of equation for I2. We'll go to our loop 2 equation and we see that I2 times 300 ohms equals I3 times 200 ohms. Divide both sides by 300 ohms and we get that I2 is I3 over 200 ohms divided by 300 ohms. So I2 is equal to I3 times 2/3. And our ohms cancel. Okay, there's another equation we have. Now let's plug our I1 and our I2 into our current law equation. So we'll start just by writing down our current law again. I1 equals I2 plus I3. Now I1, we already found an expression for that, so let's fill in what we found for I1. 0.1607 amps minus I3 times 5 over 7. That equals I2. Well, we found that I2 was equal to I3 times 2/3. And then that's plus I3 as well. Let's get all of our I3s on one side. So I've got 0.1607 amps equals I3 times 5 over 7 plus I3 times 2/3 plus I3, a little bit of math, common denominator here. 1 is the same as 3/3. can do that if you want to. So that's I3 outside of 5 over 7 plus 5 over 3. Now you can go ahead and make that a number in your calculator if you prefer, it doesn't really matter. This tells us that I3 is equal to 0.1607 amps divided by 5 over 7 plus 5 over 3. If you put all that in your calculator, what you should find for your I3 is that it's equal to 0.0675 amps. Okay, that's the current running through the 200 ohm resistor. We also want the current through the other two resistors, so let's find I1 next. I1 is equal to 0.1607 amps minus I3 times 5 over 7. But I3 is 0.0675 amps. So our I1 is equal to 0.1125 amps. And last, I2 is equal to I3 times 2/3. If we fill in that I3 is 0.0675, we get I2 is equal to 0.0450 amps. Okay, we're doing pretty well here. We were also asked to find the potential across each resistor. To do that, we'll use Ohm's law with each of the currents and the resistances that we already know. To finish up our problem now, we'll find the potential across each resistor just from using Ohm's law. So let's do our 280 ohm resistor first. The potential across our 280 ohm resistor is equal to the current through it, I1, times the resistance, 280 ohms. If you were a symbols person, you might have labeled that R1, which would be fine. So that's 0.1125 amps times 280 ohms to get, let me just make sure I got my numbers right. Yep, that's right, and that's right, 31.5 volts. And then let's do our 300 ohm resistor next. The potential across our 300 ohm resistor is the current through it times the resistance. Our current I2 is 0.0450 amps times 300 ohms. That turns out to be 13.5 volts. And last, we'll do our 200 ohm resistor. The potential is current times resistance. Our current I3 is 0.0675 amps times our resistance, 200 ohms, to get a potential of 13.5 volts. Okay, that shouldn't be a surprise that the 300 and the 200 had the same potential because they're in a single loop and they had to cancel each other out. Okay, examples we do in the future, we won't take quite this much time, but hopefully you could follow that pretty well and see what the steps are. As I recommended earlier, you might want to try this using an equivalent resistance circuit just to see that the answers do turn out to be the same.